Um, okay. Excuse me. All right, so I am going to talk through an introduction of the topic of energy and energy resources, and then the first little bit of that focus on fossil fuels. So what we're doing here is, in a lot of ways, we're continuing a similar conversation that we just started. We know about how resource consumption tends to change over time in places as economies change over time. We know how that's all related to population growth. We can think of examples related to food production and food stress, water scarcity and such. The impacts of using resources. So here it's all the same ideas, different resource, energy. Okay, so all those same themes apply. Okay, all those same trends apply. It's just a matter of understanding how they're the ins and the outs of the specifics of how the energy is being applied in these different settings. So I'm going to start with this short little thing. It's an introduction, like audio, or there's no narrator or anything. Take a look, get a quick look at different types of energy sources being used around the world, and some stuff to think about related to that. I'll just let it go here. So. Two-thirds fossil fuels. Time's up. No. I haven't watched that one, but I feel like it already makes me mad. I don't want to do it. Okay. So, across the top there, they had three broad categories: fossil fuels, nuclear, and renewables. Today, fuels day. Renewables will have their own time later on. I'll reference them a little bit here today, as will nuclear. Excuse me. This graphic illustrates a lot of the trends you were just shown on that map as well. And you can see, if you look, well, let's look at the current here, the most current, 2016, end of the graph first. Okay, that little thing about how fossil fuels are still the dominant energy source, and energy for what exactly? That's still a question. We'll get to that. Fossil fuels. What am I talking about? We're talking about coal, oil, fuels that are the result of, or are the fossilized remains of organisms that once inhabited the Earth. Right? Things found in the under the ocean that formed over the course of hundreds of millions of years. That now, last couple hundred, have been used in great amounts in a very short amount of time. So, anyway, I digress a bit. If we look at the trends, we can see coal, oil, and gas, roughly equal parts there. See how coal is kind of dipping down a little. And oil kind of leveling off a little, if not dipping down a little. And gas here in the purple, creeping up. And those are relationships, and we'll talk a little bit more about that. The renewables would be energy sources that within, on the scale of a human lifespan or generation, can be renewed. They'll come back to us in some form. They include solar and wind and some others, and you can see their little slice of the total up there. If we go back in time, we can see, pre-industrial revolution. What's the main energy source? It's labeled traditional biofuels. Any examples of a traditional biofuel you can think of? Fire. From what? From wood. Firewood. Yeah. Wood. Still here in 2016, right? A piece of the total. But pre-industrial revolution, that's what we're talking about. Firewood, biofuels, biomass. You're burning biomass. Okay? So it can be firewood, it can be animal waste, cow dung. Useful if you're got a lot of it. As the Industrial Revolution picks up steam here, we see coal become the primary dominant source. It is coal that fueled the Industrial Revolution. It is coal that drove the steam engines across the United States. Right? It is when automobiles became a thing in the 1900s there, first half of the 20th century, that you see oil become a big part of the total. Right? Coal, not the most useful thing about putting it into a car and driving around for a long period of time. A liquid oil product, though, like gasoline. And it is here even more recently, from the maybe the 50s onwards, that we see natural gas become a big part of the total, and it is the one that is very much still increasing in its consumption. We'll talk about that more in a minute as far as why that is. I should point out, and I guess I'll start off by saying this, that increase in natural gas, maybe I'm repeating myself, has everything to do with this decrease in coal, okay, and that leveling off of oil. They are very much related. We'll talk about that. All right, so energy for what exactly? And for whom exactly? First of all, I got some definitions up here, some stuff I've talked about a little bit already, just there for reference. Perpetual is this other term I haven't mentioned yet. This idea of a continuous supply, like it just never runs out, doesn't have to be replenished or anything. Kind of a rare, unique thing, sort of the holy grail, if you will, of energy. Let's think first about for whom. This is a graphic from your book. It's a collection of different countries, of different levels of economic development, different climates also represented. There's a lot to look at here. The purple bar in that top scale is total energy consumption. So just the big number, total consumption. And you would expect those bars to be big in places like China and the United States that have really big economies. Okay, India's got a big bar there, surely catching up with the rest. We'd expect that to be true. And I think at this point I'm going to bank on the fact that we sort of understand why that is. If we look at the blue bar underneath, that's showing us consumption per person. So if you look at China, they got that big total, but per capita it's really not that much. Well, China has almost 2 billion people living in it. So there's a lot of energy being consumed, but it's divided up into really small pieces for everybody. Here in the U.S., we got a big total number and one of the bigger per capitas. Okay, So this is about lifestyles here, the blue bar, affluence, right? Canada is an interesting example. Not very big total consumption compared to a lot of other places anyway. Some other places. But per capita, it's huge. What does that suggest? Well, there aren't that many people in Canada compared to other places. But per person, they're using quite a bit of energy. Pretty cold in parts of Canada for a lot of the year, for example. In Australia, kind of a similar kind of parallel example, it's really dry and really hot for a lot of the year. So per capita, we're going to spend a lot heating and cooling our homes and putting gas in our cars and driving through the suburban, urban sprawl to our jobs in the city. But total, it might be a different story. This question of like how it's related to the growth of the economy and how it's related to lifestyle. This graphic here is just showing you a pie chart form of sort of what you saw in the last graphic and the video before that. And the point is the same. Mostly fossil fuels doing what? Well, here's your breakdown by sector. Similar pie chart, or similar format pie chart for water. And water is one thing. It's a resource being used for agriculture or industry or whatever. This is a lot, right? These categories. So if we looked at it like, well, what specifically? It's generating electricity and driving all of us and all of our stuff around. That's really using a lot of the energy. Okay? How that's being applied commercially versus industrially versus residentially is broken down here. Okay? But a lot of generating electricity or transportation. Cars, trucks, buses, planes, boats, and other stuff. All right? But getting us around and getting our goods around is where a lot of it goes. What exactly is used for each of those things is another conversation. Like what makes the most sense for transportation versus heating a home versus generating electricity. Before I talk about any of that, I'm going to put this here in big, giant text because it's that important. You've seen this before. We've talked about it back whenever we talked about it towards the beginning of the year, energy and matter stuff right at the beginning. The laws of thermodynamics, right? They apply to everything, everywhere, all the time, including these systems I'm about to describe. And one thing that we're going to ask you to do quite a bit is, given this example, can you map out the information that happened? Can you identify where the energy is going if it's not going to a destination? Okay? Quantify that, and we will. We'll practice that. But all right. Everything I'm about to say is governed by the laws of thermodynamics. And a big question, therefore, is going to be just how efficient are these transformations? To get energy out of the ground, into a power, processed, into a power plant, to the consumer, involves all kinds of transfers of energy. All kinds of inputs of energy and a certain amount of output. And we quantify that every step along the way. If we're told that it's percentage efficient, we can figure out how much we'll have left at the end. And for some energy sources, that number at the end is much greater than others. You get more out for the same investment in. Okay. If you want to think about it, you can think about it this way: outputs versus inputs. What do I get? So what I put in. And I'll show you another way to think about it on the next slide. When we think about outputs and inputs, we think about costs and benefits, maybe. You can think about it that way, too. How many benefits do I get for the costs that I put in? We want to be thinking about, how much heat am I getting out for the amount of mass of energy, of material that I have? How high quality is this energy? What are the waste products involved? What do I got to do to get it? What do I have to do to get it? All of these things are associated with the costs and the inputs. And again, for some, they're going to be much greater than others. For some energy sources, much greater than others. So, the term is energy return on energy investment, or energy return on investment, if you're like brevity. And it's that same idea. How much energy am I getting for how much energy I put in? Now, I want to be clear. On that last slide, I was speaking generally about efficiency. Here, we're talking about the amount of joules in versus the amount of joules out. Okay, so same idea, but just a little bit narrower. Okay, and it's something that we want to be able to compare from one energy source to the next. This graphic here illustrates for a selected group of energy sources the return on investment, that how much we get out for how much we put in. And you'll notice, like near the top of the list, well, there's hydro. Nice. That's renewable. Then we got coal and oil. There's wind stuck in there, nuclear, right? A lot of the non-renewables live up here. It's like getting more for what we put in. And that tends to be true. It's the renewables that suffer in that regard. And it won't be until the energy out is more, or the energy we put in is lessened, or the energy we get out is increased, that those will become more popular. And that is happening. Okay, the cost of producing solar panels and such is going down as more are produced and so on. But that's a big difference right now, and historically speaking, between renewables and non-renewables, this return on investment. This graphic here is just to illustrate the idea with a specific example. The cost, anyway. The orange line is steel production going up over time, you can see. And then the blue line is the energy used to produce steel over time. The production of steel has become more efficient. We're getting more energy out. We're getting more out for what we put in. Okay. So when it comes to using oil, using coal, manufacturing solar panels, this relationship holds true. Okay. Decisions are going to be made based on how much we're getting out versus how much we're putting in. Kind of a big idea. So, what exactly is involved with producing electricity? I mentioned how producing electricity is a big part of that total. And there's the total used is for commercial electricity generation. Commercial meaning produced by a utility for sale to people, the public, businesses. That would be, conversely, have subsistence production, which would be putting a wind turbine in your backyard and solar panels on your roof, right? You're creating energy at a subsistence level versus a commercial level. At the commercial level, this is one way to do it, but these are all the same. You'll see in other models as well. Basically, what we're doing is this: we're burning a fuel. It's coal. Coal is the first choice, historically speaking, I should say, was the first choice for this kind of thing. We process the coal, we burn the coal, and in burning the coal, we're heating water, and we create steam. The steam spins a turbine, like a fan spinning, and that spinning turbine generates electric current. All right. Funny things happen when you create a magnetic field with spinning metals. Electrons start moving in a direction all together at the same time. It's called a current. And that's what we're doing. We're generating current by spinning this turbine. How are we spinning it? By burning coal and producing steam. We get to coal to the power plant, and then we got to deal with what's left afterwards. Okay? But the return is still pretty great. Right? We're still getting a lot out for what we have to put in. Coal is pretty easy to find and pretty easy to use. This is a real-life picture of one of these things. They look surprisingly similar if you look around. Okay, so how can we increase the efficiency of this system? Right? How can we get more return on our investment? Well, we can increase efficiency along the way with all of the energy transfers, right? That's one way to think of it. We could limit our waste, maybe, right? Another way to think of it. Well, one way that happens on a fairly large scale is called cogeneration. That steam that's produced to spin that turbine in a sort of a conventional type power plant, that steam is condensed back and then really hot water is disposed of to the environment. That's a pollutant. It's also really hot water that might be useful for something, like, for example, heating the building that it was in just a few minutes ago, or heating the buildings that are nearby, for example. These graphics are from a story written in the Toronto Star newspaper. They built one of these things in there, kind of a urban space there in the inner harbor. And what's happening in a cogeneration plant is you're producing electricity, much like I just described, but that hot water, instead of being wasted, is being used to heat the power plant or to heat the buildings. Same coal, investment of coal, two outputs: heat for the buildings and electricity. Okay, cogeneration. To do it. This work, you're not going to take that water, transport it hundreds of miles to some other place to heat that place. That's not how this is going to work. But in these examples on scale, it's a pretty reasonable way, pretty easy, kind of low-cost way to get a lot of return on investment, or really increase your return on investment. Okay, so efficiency, right? When we think about these systems, we want to think about it in terms of efficiency. We want to think about energy transfers, how to increase efficiency, and so on. We want to be able to identify, from place to place, what to expect as far as energy consumption goes, from developed countries to developing, and so on. Here, we're going to start talking about exactly what these things are. What is coal? What is oil? And so on. And what are they specifically used for? Okay. Just mentioned as an example, generating electricity. But what about the other stuff? Times this class. 15 after? 2:50? All right, I'm going to show you this. I think I have time. Where's my cursor? There it is. This is just a quick little animated thing showing you where coal comes from versus oil and so on. Okay, I'll revisit a little bit of it here in the next couple slides, but here we go.
Fossil fuels. Fossil fuel is a term used to describe a group of energy sources that were formed in ancient planetary formations during the Permian period 286 million years ago, even before the age of dinosaurs. At that time, the land was covered with swamps filled with organisms and plants. As they died, they sank to the bottom of swamps and oceans, and over millions of years started decomposing under layers of sand, clay, and other minerals. Different types of fossil fuels formed depending on the combination of organic matter, temperature, time, and pressure conditions while decomposing. There are three major types of fossil fuels: coal, oil, and natural gas. Coal was formed from ferns, plants, and trees, which hardened due to pressure and heat. Oil was formed from small organisms, like zooplankton and algae, where pressure caused more complex organic matter to decompose. Natural gas was formed by the same process as oil, only it was exposed to more heat and pressure, causing it to further decompose and turn into a gaseous form. Fossil fuels are sought-after energy sources because they have a high energy density. They are the world's dominant energy source. Fossil fuels have a variety of applications in electricity. They can also be used to make a variety of common products, from plastics, cosmetics, to even medicines. These resources have powered industrialization over history and continue to do so today. Fossil fuels can be abundant and cheap, or in some cases, a scarce and expensive form of energy, depending on geographic location. For this reason, geopolitical issues arise due to scarcity caused by the natural geographic allocation of these highly valuable resources. Fossil fuels are considered non-renewable resources because they take millions of years to form, which means that once they are used, the resources will not be replenished in a human lifetime. The gradual depletion of the most successful fossil fuel reserves forced companies to develop technologies for extracting more challenging or unconventional reserves. In many cases, this means additional safety and environmental concerns as well as higher costs. Fossil fuels are also the largest emitters of carbon dioxide, a greenhouse gas which causes. In addition, their production causes environmental and human health issues. These concerns encourage society to look at alternate sources of energy that are more environmentally sustainable and renewable. That's fossil fuels.
All right, so, come on now. What's going on? There we go. Oop. Oh, gosh. Okay. So, coal. Said it already. Coal was like the original fossil fuel, right? It's the one that it's still the most abundant, and it is extremely energy dense. It's easy to use. We don't need to refine it a whole lot. We take it out of the ground, and it's pretty much ready to go. There are different kinds of coal, depending on how long and under what amount of pressure it was exposed. But it's a good one. It's the most dense. It burns the hottest and such. But all of them are what we're going to call the dirtiest of the fossil fuels. And the reason we say that is because it's not just about carbon dioxide, which is a greenhouse gas and the driver of climate change, as we understand it, but it's these other things. The heavy metals like mercury and these sulfur compounds that end up in the air and the water that have really detrimental effects to living things. There's also this question of the waste. That ash produced by that coal power plant is not a small thing. In fact, image and some description of an event that happened where these ash storage areas overflowed, and you can see this house is just buried in the stuff. So that's a significant issue as well. It is the first choice for power plants, although that's been changing with the increasing supply of natural gas. Coal-fired power plants have actually been converted in some cases, which is a reason why, like when I don't want to get overly political, but when the current administration came in, there was talk of kind of like revitalizing the coal industry because it was struggling a little because natural gas was kicking its butt, and a lot of people came back and said we already changed. We don't have a coal power plant anymore. This isn't our choice anymore. So that dip in coal you see on that graphic there has to do with an increase in natural gas, it being cheaper and cleaner. That cleanliness part is important. That's becoming more of a thing for more people. And it's becoming more of a reason at a governmental level and so on to make decisions that move us away from coal. And that's been going on for a while. If you go a graph there, back into the pre-2000, right? It's been going on for a while. Coal, it's interesting. The Carboniferous, this period of time that was described in the video, this is a period of time that is the Earth is warmer. A lot of tropical forests are covering the land masses. And this is the remains of those tropical forests. You find a lot of coal in China. You find a lot of coal in the United States. You find a lot of coal in Russia. Big country, not surprising. That is where a lot of the coal reserves reside. Coal mining can happen. It can be what maybe you're picturing, like a hole in the ground and you got your headlamp on. Coal mines like that certainly do exist, many of them, and human health is the concern there. It's a huge concern. It's not a very highly regulated place, and even when it is, it's a little dicey. I'm showing you these pictures because I couldn't talk about coal mining without bringing it up. This is another way to do it. These pictures are from West Virginia. This one got a little blurry when I blew it up, but it's exactly what it sounds like. They blow off the tops of mountains, take the coal, and then push the leftovers into the valleys below. And it makes it easy to get the coal, but there's all kinds of that's now at the tops of mountains that's going to wash down. All kinds of water that comes out of that. It's a really, really impactful process, both to people and ecosystems, to get coal. But once we have it, that's pretty much it. It's easy to use after that, and that's the draw. Petroleum is what we call oil when it's still in the ground. It's petroleum. When it's out of the ground but unrefined, it's crude oil. Crude oil is refined into all kinds of different things. This graphic came from a place in the UK, so they spell some things a little differently. But what you do when you refine oil is you're doing distillation. You're heating up increasingly to higher temperatures, and as you hit boiling points of all of the different elements or compounds in the mixture, those things boil off and you collect them. Down to asphalt. And you can see all kinds of different petroleum products. But a lot of oil, or different types of fuel, I should say. And the reason this became a really widely used energy source was driven by the advent of automobiles and other kind of transportation-related needs. Coal's not real easy to pack up and take with you. Those trains that went across the country were multiple coal cars, carrying all of the coal we needed to get there. Here we can fill our tank with a liquid, a really energy-dense liquid, and go great distances in pretty short periods of time. So that's the advantage. It is, while it's not as quote-unquote dirty as coal, it has similar types of issues burning petroleum does. Right, we still have the carbon issue. We still have the mercury and metals issue, although to a lesser extent, often anyway. But it's the sulfur thing that's not an issue. You can actually remove sulfur during refinery. It makes it more expensive, but it's something that happens. It is, it's a reason why we would consider it to be cleaner. This graphic is here because I like it. Your book has one too. You just saw one on there. I'm not going to break that down much more. But oil and natural gas tend to be associated with sedimentary rock formations because of where it came from. It came from the bottoms of oceans, or areas that were at the bottom of the ocean at one point. Natural gas is found with oil. They go together, usually. Increasingly over time, we found other places to find natural gas, and that's something I'll talk about here in a second. Gas is considered the clean one. It's the clean one. It's an issue. That's less, right? There's not as much carbon dioxide produced by burning the same amount of natural gas as coal. But we have other impurities, which is a big deal. The issue with natural gas is that the methane itself, the gas itself, gets into the atmosphere. And that is a really potent greenhouse gas, methane is. More potent than carbon dioxide. What's also true is our decisions to go get natural gas in these new kind of unknown ways, unknown meaning like a lot of that's happened really fast. A lot of that we're going to find out about in the future. We don't know yet. What is undeniable is the fact, our decision to go to get natural gas through this hydraulic fracturing method has so greatly increased the supply and dropped the price that there's a lot of momentum there. It's going to be hard to suggest that we do something else. Your book doesn't make a big deal out of fracking, and I can't wrap my head around why, other than this wasn't when they published the book. It happened so fast. Like this part, look at North Dakota. This is North Dakota. Okay? Nobody lives in North Dakota. I don't know if you knew that. It's like nobody lives there. There are a million, more people live in St. Louis than North Dakota. I'm wrong about that, but it's close. But look at this. What's going on there? Well, what's going on there is natural gas exploration, and it's really, really fast. Like in the matter of weeks and months, this just exploded, and it's been going on for a long time in the eastern country, Pennsylvania and such, and more and more you hear about it popping up other places. What we're doing is we're harvesting gas from these underground rock formations where it's been trapped in these little pores. Water at really high pressures and all kinds of chemicals to loosen stuff up, and we get all kinds of gas. But we have all kinds of unknowns, like I've been saying, related to that. So to be determined on whether or not that ended up being worth it. In terms of oil, we are once again going to kind of a lesser quality reserve in the form of these oil sands. These are places that either or it just wasn't worth it. Like we go other places that's easier. Why? Let's not do this. Well, demand remains high, and therefore that demand has pushed us to do these find oil different places. So oil sands are these really shallow deposits, excuse me, and they occur over these huge areas. So to get to them, you need to disturb huge areas. And that's exactly what's happening. These are images from Canada, from kind of the central part of the country. And Canada, because of this kind of thing, is our biggest supplier of oil. It's not the Middle East. The supply of oil has, the domestic supply of oil has really increased quite a bit because it's much like it has with natural gas. The trade-off, huge environmental impacts. Cost is greater too. It's harder to get, so therefore it's going to cost more. With the case of gas, that's not so much been the case. We've been getting so much more of it that for relatively easy that the cost has actually been going down. Okay, almost done. Turns out, and I'm going to be honest, hopefully this is obvious at this point, but at some point we are not going to be able to use fossil fuels anymore. Okay, that's been known for quite a while. The question is, when? Good news, it might be within your lifetime. Just last class, somebody was looking up at the end of class, 53 years is this one projection they saw. I feel like I don't know about that. We'll see. But the point, this is an interesting idea, and it's something that needs to be thought about. Hubbert's curve is what you're looking at here. And it's an interesting idea. No matter what we do, here's my summary. We're going to run out at about the same time. Whether we increase supplies or not, whether we find more or not, we're probably going to run out about the same time, because what tends to happen is when we increase our supply, we just increase our consumption. That's been the trend. What's also true is more and more you're finding that governments and people and society kind of in general is concerned about the environmental impacts of using fossil fuels, so they're going to consume less and less. So we have these kind of competing things, like what's it going to be? Are we going to run out, or are we going to choose not to? Well, this is suggesting that the end target, the end result, end up being about the same because of behavior, because of what we tend to do. We tend to use more when we can. So, whatever you think of that, however that makes you feel, fossil fuels are here. They're not going anywhere immediately. You can't just turn them off. That's not how that works. There are entire populations of people all over the world that completely depend on them. Their hospitals run off of them and such. Right? We can't just stop using them. But where and who and how this transition happens is a big question. A lot of it's going to have to do with supply and demand. Like, do you have it or not? What are your options? But also values, like we've been talking about. How is this resource valued? Well, it's valued differently over time as its supply gets less, but also as other options become more viable. So there's a lot to think about there. A lot we will think about in the future. That's a story for now, I guess. We have, let's see, a few minutes. So, any questions? Where's my, oh, I'm sorry, I'm going the wrong way. It is this I want. Whoops. Okay. So, next time we're together, what we're going to do, you were given a reading to look at, to read after your assessment, hopefully. If you didn't get one, it's on Canvas. Energy use in the United States. You've got your textbook to read, of course, also. But next time we're together, we're going to spend some time with math. We're going to spend some time learning about what units of measurement we use for energy and electricity and how they, just the basic kind of dimensional analysis stuff. And some application stuff regarding efficiency, because those are important skills that we got to practice. So we'll do some of that. We'll also do some, we'll talk more about this idea of consumption patterns, and we'll try to make some connections back to the population stuff and the agriculture and water stuff that we've been talking about. As an example, before we go here, last few minutes, this is the kind of thing we're going to ask you to do. How many watts of energy are needed to power a 100-watt light bulb if the following is true? Electricity production is 38% efficient. Transmission across power lines is 85% efficient. And the light bulb itself is 5% efficient. I want you to think about how you would solve that. Mapping it out on paper might help. See if you can come up with an answer. And then you may go. I'll put these back before I forget. I wish I had a whiteboard. I forgot. I meant to bring one. What do you think? Anybody know yet? What do you think? Sorry, say it again? Over 6,000? Agree, disagree? Anybody? Why are you not doing it? Are you all going to complain about how you don't know how to do the math problems when we have our next test? You're going to sit here and not do them? It's getting a little old, to be honest with you. Oh, gosh, hang on. So you can think of it this way. It's about 1.6% efficient, meaning that if... well, are we out of time? Yeah. We're out of time. All right. More on this later. I don't want to talk circles right now or get myself confused.